Homework 15, sampling distributions in the central limit theorem, video 4. This is actually the last video in this series, which is good because one of them was so freakishly long. But it shows an example of how this type of probability is actually used in industry. A roller coaster can hold 60 people. They built it that way. The maximum weight it can accommodate is 12,000 pounds. According to the National Health Statistics Report, which is a real thing, the average adult male weighs 194 pounds, with a standard deviation of 68 pounds. Not sure where they got those numbers, but let's go with them. If 60 adult males ride the coaster, what is the probability they will exceed the weight limit? These are important things that engineers consider when building things that could crash and kill you. Roller coasters, elevators, trains and buses, things like that. So, first off, where do we even begin? Well, there are some things in here that we were given that we can immediately identify. For example, the average adult male weighs 194 pounds. So we're being told that mu equals 194 for men. And the standard deviation is 68, so we can go ahead and say standard deviation is 68. And we're picking 60 males out of all of them. So 60 is our sample size, which is good because that's at least 30. That guarantees the X bars are normal. But what does it mean in terms of X bars that the 60 adult males exceed the weight limit? Well, let's think about what it would mean if the 60 adult males hit the weight limit exactly. So in other words, if there are 60 males and they weigh 12,000 pounds, on average, what would they weigh? So on average, each rider can weigh 12,000 divided by 60, which is exactly 200 pounds. So if the average weight of the riders is 200 pounds, then that's going to be a total of 12,000 pounds. So we don't want to exceed an average weight of 200 pounds for the riders. So what would it mean for the 60 adult males to exceed the weight limit? Well, the highest average weight it can sustain is 200. So to exceed that, the average weight would have to exceed 200. So we want to know the probability that the average weight of these 60 males is more than 200. Because if it is, then their combined weight would be too much. Let's just draw a bell curve for this real quick to make sure we know what we're looking for. The bell curve for the X bars. And remember, the middle of the bell curve is always its average, and the average of all the X bars is just the average of the population, which was 194. And the standard deviation of this bell curve is not 68, but rather 68 divided by the square root of 60. So let's figure out that. Your square roots are usually not cooperative like the one I had in the last video. So what did I do? I just typed 64 instead of 60. So 68 divided by the square root of 60 is approximately 8.7788. We'll take it to 4 decimal places. And we want to know what's the probability that the average weight of the 60 riders would be more than 200. So we'll put 200 over there. Which is equivalent to asking what's the probability if this is all adult males that the thing's going to crash. Hopefully pretty low. And by pretty low, I mean really low. Okay, So all we have to do is to convert this to a z problem, the probability that z is greater than something. And so let's go ahead and sketch the z curve for that. Oops, z wouldn't go there, 0 goes there. I know I'm looking for some number to the right of 0 because over here is to the right of center. But in order to use our z chart, we have to convert to a z value. So this 200 represents an x bar. It's a number that we're comparing the x bars to. And we have to convert this. I'm going to go and write the formula one more time. Z equals x bar minus mu sub x bar over sigma sub x bar. We have all three of those values. We're converting 200. The average of all the x bars is 194 because it's also the average of the population. And the standard deviation of all the x bars ended up being 8.7788. So the top number is 6. The bottom number is 8.7788. And so the z value is to 2 decimal places, 0.68. And remember, we only need 2 decimal places because our z table can only accommodate 2 decimal places. The left column are the digits on either side of the decimal. So we go to the 0.6 row. The top row represents the second decimal in the z. So we would go over to 0.08 and then see what the area is there. So what is that area? Dude, I know what some of you are saying, I'm not up in the right book where I have my z table. And by the way, if you happen to have a hard copy of the book, it's back in the appendix, after the index, where the tables are. But if I look up 0.68, the number I'm going to find is 0.7571. Why can that not possibly be the correct answer? Think about it. We're looking for this area over here. If we cut it right down the middle, that's exactly 50%, or 0.5. So this area in the right tail should be smaller, not larger than 0.5. So why do we get an answer that doesn't make sense? Because our z table tells us areas to the left of things. We are looking for a right area, which means what we found is not what we want, but what we don't want. In other words, 0.7571 represents the area over here. And how do you find the area of the right tail when you know the left? Let me try that again. How do you find the right area when you know the left area? You subtract from 1. So we need the probability that z is greater than 0.68. And it's going to be 1 minus this left area. And this is a disturbing number, 0.2429. Or as a percent, 24.29%. That seems a little high. Luckily, this question was an odd question in the book, so I can just flip to the back and see what they said the answer was. That's a little disturbing. What that's implying is under these conditions, if 60 adult males rode this roller coaster, there's about a 25% chance, a little less than 25% chance that it's going to exceed the weight limit. Now, does that mean the thing's going to come crashing down? Probably not, because when they set those weight limits, they actually set them much lower than what the roller coaster could actually tolerate in case something like this happens. So this is just me talking. This is 7.3, number 27. Well, they got 0.2483, which is close, but it's not close enough for my liking. If they got 0.2483, then the left area would have been 0.7517. Did I just look at the wrong place? Did I misread it? 0.68. Yeah. I just, oh, I see what I did. I transposed 2 digits. Sorry, temporary dyslexia. I'm not going to redo the whole video, but when you look up 0.68 in the z-chart, the area was 0.7517. I think I miswrote it when I erased this and wrote it there, which would make this 1.7, which would make this 8.3. So 24.83% chance, which is still scary that if 60 adult males, like 60 college males, rode this roller coaster, there's almost a 1 in 4 chance that it's going to be too heavy, and who knows what will happen. But in industry, they actually calculate things like this to minimize the risk of a catastrophe happening. In this case, they did a horrible job of minimizing this risk. Honestly, I was expecting this to not even be 1%. The fact that it's that high tells me that either A, this problem was just made up, or B, somebody's really bad at designing roller coasters. All right, I just want to summarize what happened real quick. When you're doing a probability involving a sample mean, and I'll admit in this problem it was a little stealthy because nowhere in here does it mention the sample mean. We had to think about what would it mean to hit capacity in terms of average weight. And by the way, there's a homework problem similar to this one. I think it's about elevators. But if you're going to do a probability involving an x bar, then you have to convert it to a z, and the formula for converting it is this. On your next test, you're responsible for using your own notes. That better be in it. Once you convert it to a z problem, then you just attack it as such. In this case, it was a right area, so it was 1 minus the left area. And if the whole right area and 1 minus left area thing doesn't make sense, go back, rewatch the videos for 7.1, try that homework again. Don't just go through the homework and click view an example to get right answers. It will kill you on your test. All right, so that's the end of this series of videos. A fairly short one, but it is what it is.